So on the first section of this unit on proportions, we looked at ratios, and today we're going to look at rate of change. So in this first example, Alicia likes to collect teddy bears. The graph shows the number of teddy bears in her collection between 1997 and 2002. So the first question asks, by how many? We look at the graph and we say, by how many bears did Alicia's collection increase between 1997 and 1999? All right, so look, I have 1997, 1999. How much did they increase? They increased from 8 bears up to 22 bears. Okay, so to find out how much they increased, I find the difference between those two numbers, 22 minus 8, and I find that there were 14 bears. So it increased by 14 bears. How about between 1999 and 2002? That's the next one. Okay, so here's 1999, here's 2002, and now, again, find the difference between those two numbers, and 37 minus 22 is 15. Okay, so the question is, between which years did Alicia's collection increase the fastest? Was it between 97 and 99 or between 99 and 2002? So I hope that when you were looking at this, you weren't just comparing the 14 and the 15. A lot of people are tempted to do that and say, hey, look, 15 was bigger than 14, so it looks like Alicia's collection was increasing the fastest. But we have to think about how many years had passed. So between 1997 and 1999, that's 2 years that go by, and we increased by 14 bears. Well, 14 bears in 2 years means about, on average, how many bears per year. All right, so finding a rate of change is something that you guys have done before as finding a unit rate. So I know 14 bears in 2 years. How many bears in 1 year? Well, I can do 14 divided by 2, and I'm going to end up with 7 bears per 1 year, or 7 bears per year. Okay, now I want to do the same thing for 1999, 2002. Again, we know that it was 15 bears, so I can write 15 bears. And I know this time, 99 to 2002, there were 3 years that went by. So I'm going to divide it by 3 years. And again, what's the average per year? 15 bears in 3 years means that there's going to be 15 divided by 3, or 5 bears per year. So which one was faster? Was it faster when it was going 7 bears per year or 5 bears per year? It was when it was going 7 bears per year. When was that? And that's between 1997 to 1999. So what is the rate of change of Alicia's teddy bear collection from 97 to 99? That's the change in bears over the change in years. We already found that as 7 bears per year. What does this rate of change tell us? Well, it tells us on average her bear collection grew by 7 bears each year. That's each 1 year. So that is a unit rate. How many we want to know? So the rate of change is finding a unit rate. How much does it change each 1 year? Okay, let's go ahead and answer the next one. Okay, now we're looking at a table that's showing Ramon's height in inches between the ages of 8 and 13. And we're going to find the rate of change in his height between ages 8 and 11. Okay, so between ages 8 and 11, it's first of all, let's make sure that we're finding the right thing. We're looking at 8 and we're looking at 11. We're finding at the rate of change between those two ages. All right, so before we basically looked at the difference between the two heights, and this time I'm going to write it out kind of like a formula here. We know that he's going to grow up to 58 inches, but he starts at 51. We're trying to find the change in height, which we find so I'm going to write change in height, and we're going to have to divide that by the change in years. I use this triangle here. This is actually the delta sign that actually means change. If you want to write the word change in there instead, or get used to the delta, it's actually a Greek symbol there. And you may see that if you end up joining a fraternity or sorority, you know what delta looks like. It looks like a triangle in there. But it means, it's used a lot in math, and it means change. So we're looking at the change of height divided by the change in years. So how do we find the change in height? Well, we start off with the newest height, which in this case is 58, and we're going to subtract the old height, which is 51. Same thing with the years. We start off with the newest years, the newest time, and we are going to subtract the oldest age, or not the oldest, but the older, longer ago. And then we do, and so this is again, these were inches, these were years. And so what we found is we have 7 inches when we did 58 minus 51, and we did 11 minus 8, which is 7 inches per 3 years. So once again, we're going to have to do the 7 inches divided by 3 years. And this one doesn't work out so nicely, but we do know that we are going to have 7 divided by 3, that's inches per year, so 7/3 inches per year, or we could, 7/3 is actually 2 1/3 inches per year. And we could write the word per, or we could put a slash down there to show that it was inches per year. So 2 1/3 inches per year. All right, go ahead and do the same thing, but this time you're going to be finding it between the ages of 11 and 13. Go ahead and see if you can find the rate of change between 11 and 13 and see if you get the same thing that I do. Okay, so I found the change in height and divided that by the change in years. How did I find the change in height? I did the new minus the old. In this case, we have the new was 67 inches minus the old, which was 58 inches. And then I did the new time. So the person was 13 in the newer time, minus 11, which is the older time in there. And I do that subtraction, and I ended up with 9 inches per 2 years, or 9/2 inches per year, which changed to a mixed fraction is 4.5 inches per year. So I took the table of Ramon's height and age, and I put it into this graph. And let's take a look. And then I wrote what we found already in terms of, we know the first part from ages 8 to 11, he was growing at 2 1/3 inches per year. And we knew that between 11 and 13, he was growing at 4.5 inches per year. And let's see if the steepness of the graph makes sense with these numbers. Where is it steeper? Is it growing slower and then faster and getting steeper? Or is it growing faster and then slower? Which of those made more sense? Which of those happened? And how does it match up with those numbers? Does it make sense in this case that we have 2 1/3 inches per year? 2 1/3 is a smaller number than 4.5, so we'd expect it to be going at a slower pace of growth. Here is slower. Here it's getting steeper because it is growing faster. We are comparing that unit rate, that change if we go back here, we're looking at the rate of change here. And if we are looking at here, the rate of change is becoming a bigger number. Where is it here? The rate of change is becoming a bigger number, and the steepness of the slope is getting steeper. That goes with it. In fact, that rate of change and the slope, which is where we're going to get into our next day, we're going to start talking about our slope. Those two things are very much related and can be even considered the same thing. It's a unit rate. How many inches is he changing each year? That is the slope of this line, and it is the rate of change for these parts of the line. So on number 7, we're looking at a graph that's showing cassette sales from 1994 to 2000. When I was listening to music at this time, we had cassettes. You guys probably have seen them. They look kind of like this in here, and that's what I put into. It wasn't digital music. We had a little tape thing that would kind of spin around. These things would wind, and that's how we listened to our music back in the 80s and 90s. But slowly in the 90s, the compact disc, also known as the CDs, took over, and the sales of cassettes went down. So A couple of things. One, you can see I put the big red X's on the graph. Somehow the computer put in the wrong numbers in there, so I wrote them in blue next to the ones that are correct in there. So we're trying to find the rate of change between 1994, the first, in part A, we're trying to find between 1996 and 2000. So we're looking at 96, which is right here. And in fact, here's the number that we're looking at, and the year 2000. We're basically comparing, we're finding the rate of change for this thing. Now, we're going to do it's the new minus old over the new time minus the old time. So I have the new, which was 4.9 million. And I can just, if I can remember million, this is really important that over here it said millions of dollars. So a lot of students are leaving off the millions, which is obviously crazy, because if you're just writing it in dollars and millions of dollars, there's a very big difference between that. So I have $4.9 million is my newer value of money. And I'm going to subtract the older one, which is $19.3 million. And I'm going to look at the newer time, which is 2000. And I'm going to subtract the older time, which is 1996. It's totally okay. This is a calculator unit. You're welcome to use a calculator to do these subtractions in there, and then write down your answer, and then reduce this and to find the rate of change. So I hope that you didn't leave the units off there. We found the rate of change between 96 and 2000 to be negative $3.6 million per year. In other words, every year the sales went down by $3.6 million. And we have a negative rate of change, which is compares in our graph. When we look on here, we actually have a slope here going down that is going to give us a negative slope. But in this case here, it is a negative rate of change, negative $3.6 million per year. Okay, see if you can answer parts B and C. Now we're looking at between 94 and 96, looking at the rate of change between those 2 years for part B. And for part C, we're looking at actually the whole thing from 94 all the way to 2000 to find the rate of change between those two for part C. So go ahead and do those two, and then check your answers with mine. Interestingly enough, between 94 and 96, the sales of cassettes was going down faster than later on between 96 and 2000. Those people who held on to their cassettes wanted to hold out as long as they could before they switched to CDs. And so those holdouts, kept buying cassettes until really they stopped making machines that would record cassettes for you. And then we all really had to switch over to CDs at that point. And it also interesting in that if you look at C, the negative $4.63 million per year, that one is kind of in between. If you think about the first one as being, the later one as being negative $3.6 million per year here, and this is being a steeper negative $6.4 million per year, then going from here to here is actually going to be somewhere in between the two of those to find that rate of change. And sure enough, negative 4.6.3 is between those two numbers. All right, let's look at the last two questions here. We're looking at the cost of a first-class stamp. That's the stamp that we use to mail a regular letter in the United States. And what are the time periods? For what two time periods did the cost of a first-class stamp not change at all? Go ahead and write down your answer for that. So I can see it right here. Between 92 and 94, there was no change. And between 96 and 98, there was no change. So I'm going to write those answers there. 1992 to 1994 and 1996 to 1998. Now let's actually find that rate of change between these two here. Between 1992 and 1994, let's find that rate of change using the same formula. We're going to do the new minus the old over the new date minus the older date. Let's go ahead and calculate that. And sure enough, we find because there was no change, the new rate was 29 cents, and the old rate was 29 cents as well. So I do 29 minus 29 gives me 0. The change in time is going to be 2 years. 0 divided by 2 gives me 0 cents per year. The rate of change when it doesn't change makes sense that when it doesn't change, the rate is going to be 0. 0 cents per year.